Hey guys! Well, exciting, right? I hope you guys are all safe and sound inside your houses and not dealing with the crazy icy snow. Here's my plan for you. Right? Obviously, you have now Friday, Saturday, and Sunday to get the lab completed that you have been either working on in class, or if you weren't in class, there's an online document on the Moodle for you to complete. So one of those two things will be due Monday. The topic we have kind of hanging out here that I was planning to tackle on Friday, they'll be moved to Monday, but I need you guys to do a little work on, is starting with the math. Okay, the combined gas law versus the ideal gas law. And you had a video on Thursday night over the combined gas law and ideal gas law, and I got lots of questions already on it. So basically this is going to be a video on the ideal gas law and the combined gas law again, explaining some of the questions, showing you some of the problems so that on Monday we spend a little time on this, but then we can also move forward. Okay, so if you're in class or if you've been doing the simulations, remember that in all these situations, we have some gas at some condition. Okay, some pressure, some volume, some temperature. You alter one of the variables, and as you alter one, the other one will change. Okay, those are the gas laws. For Boyle, it's a pressure-volume relationship that is established, that as pressure goes up, volume goes down. For Charles, it's a volume-temperature relationship. As volume goes up, temperature goes up. And for Gay-Lussac's, it's a pressure-temperature relationship. As pressure goes up, temperature goes up. So essentially, you have three equations that are your gas laws. But we combine those into something called the combined gas law, and that's what's on the screen here. Combined gas law allows you to do problems in changing situations. I have a gas at some situation, I change a variable, here's how all the other variables are affected. It's independent of number of moles, it's independent of identity of gas. It doesn't matter what kind of gas you're measuring. If there's a changing situation, you use the combined gas law. Then we also have something called the ideal gas law. And the ideal gas law deals with gases in a static condition. If we include number of moles into our equation, which is N, then PV, N, and T all have a relationship, which is R. Okay? All along the way, we've been showing that it's a constant. As pressure increases, your temperature also increases at a constant rate. Basically, the relationship pressure, volume, number of moles, and temperature have with one another is the constant R. It's the factor that we use that allows us to get the correct values. And also, it's the factor that we use that allows us to, take a volume and make that into a temperature somehow. Right? Usually, to convert one type of unit to another type of unit, you need some kind of conversion factor. Well, this equation has a constant that allows you to switch types of measurements. Okay, simple as that. This equation is used in a static situation. Situations where your gases aren't changing, it's just a snapshot of the moment. Okay. So what I want to focus on is this question. How do you know when to use the ideal gas law and when to use the combined gas law? And on the form for video number 4, I had these two questions that people were supposed to answer. And some of you have gotten it right, but I've gotten a very wide range of answers in terms of what was right and what was wrong. So I'm going to walk through these two problems as our example problems for how to do a combined gas law problem and how to do an ideal gas law problem. And then on Monday, we'll do some of the harder problems together. Make sure you can do the other two components of the combined gas law, which is understand the relationship and explain the relationship. Right? And then we'll move forward with some more content. I still kind of have your tests scheduled for Thursday in my head, but it may get pushed to Friday. I'm going to talk to my co-teacher again and see what he thinks. But right now, we're still shooting for Thursday because I think we can get through the content if you guys put some work in today, Saturday and Sunday. So here are the two problems that were on the form. And we're either dealing with a combined gas law problem or an ideal gas law problem. I'm going to show you how I set up every problem and help you figure out how you will know which type of problem it is. Okay. So let's tackle the first one first. As I read through all of the variables, I see temperature, I see pressure, I see temperature again. If I see any measurement twice in terms of pressure, volume, or temperature, I know that's a combined gas law problem because seeing the variable twice means it changed. Changing situation means combined gas law. Don't put your tongue on
Hi, I'm Amelia.
So if you have a changing situation, that is your combined gas law. And your combined gas law, one side has all of your three variables in some kind of initial situation, and the other side has all your variables in a new situation. Basically, it's a ratio. We're saying the degree to which any variable changes, the other ones will change also to keep this equation equal. So if I set up this problem, I'm going to have some initial condition with my initial variables and some new condition with my new variables. I read the problem and I just start assigning. So the pressure initially is 3.13 atm, and the question is, what's the pressure after? The volume information isn't given, so I can just erase it because it's not one I need to worry about if it's not identified. It means that it's constant. The temperature given is 66.4 degrees Celsius, but anytime in these problems you have a temperature, you have to make it into Kelvin. If you don't make it into Kelvin, you may end up with a negative pressure or a negative volume, which doesn't exist. Okay? So to get to this to Kelvin, you add 273 to it. If I add 273 to that, I get 339.4 K. I'm going to do the same thing with my second temperature of that negative 9. So 273 plus negative 9 is 63.9. Now it's just a question of plugging all these numbers into the equation and solving. So P1 is 3.13 atm. I don't have a V1. I divide that by the temperature initially, and that's going to equal some pressure I don't know divided by what the temperature is in the new conditions. So to solve for this variable, it's just a question of algebraically rearranging. You take this divided by this, and you multiply this up to this side to get P2 by itself. And if you do that correctly, you get that P2 equals 2.43 atm. Some people have been asking, how do you know what pressure unit to use? ATM, KPA, millimeters of mercury. Whatever I give it to you in, it comes out in, so don't change it. If I ask for a different one, I'll give you the conversion factor also. And you can see how units cancel here. If you take this divided by this, you'll have ATM divided by K. But multiplying this up means the K's will cancel. Okay? Because you'll have a K on top, right? You'll have a K on top, and you'll divide by K also, so those go away, and your final unit left over is just ATM.
Mom, what songs do they know?
They know any song you know. Sure. If I read the second problem that was in the form, I start reading and I see, okay, I have a temperature, I have a pressure, I have a mole, and I ask for volume. So oftentimes I double check and run through it again. Do I have any condition given to me twice? Temperature, pressure, volume, mole. No, all I do is define each variable one time. And if everything's just defined one time, that's an ideal gas law. I'm taking a snapshot of the gas, and I want to know one of the variables that aren't defined. So this is a static condition. Things aren't changing. I have 5 variables I need to define, P, V, N, R, T. And then I just identify them from the problem. My pressure is 3.13 atm. My volume, as given to me, is something I don't know. My N is given to me as 1.41 moles. My temperature, as given to me, again, needs to be converted, which we already did. And then we get to our R, our mystical, magical R. You'll have 2 R's that are constants. Those are numbers I'll always give you. You need to have the equations memorized. The R you choose is solely dependent on your pressure. If you look at all the units of R, back when I gave them to you, they're all measured in liters. They're all measured in K. The difference is one is measured in ATM, one is measured in kPa. So choose the appropriate one based on the pressure that's defined in your problem. The correct R for this problem with ATM is 0.0826. And then the units on R is ATM times volume over mole times K. Now remember, this is just a unit. Okay? It's just a way to make all of our numbers mathematically cancel out so that we have the correct units in the end. Now you just plug in and solve. If I have 3.13 ATM times some unknown volume, that equals N, which is 1.41, R, which is a constant, and then T. My board is very small. Okay. Solve for V, take this times this times this, divide by ATM, and you get volume by itself. Okay, so if you solve this correctly, you should get a volume equal to 12.5. If you're like, what are my units for that? Your units come from R, okay? You had pressure get canceled out, moles get canceled out, temperature get canceled out. All you have left is liter. So that is the unit then for your volume. That's how you tell which equation to use, combined gas law or ideal gas law. Remember again, the combined gas law came from your gas law equations, Boyle, Charles, and Guy-Lussac's laws, which you need to have memorized their relationship, and you have to have the equation memorized, which is why I showed you that triangle. That triangle is a really easy way to memorize whose laws is which one. Okay, because again, if you stick these variables into a triangle, it's alphabetical on the outside. Boyle's is PV, Charles is VT, Guy-Lussac's is PT. Then you know which variables are assigned to which guy, and that'll get you at least one of the multiple choice questions, right? And then another multiple choice question will be relating the two variables to one another as pressure goes up, volume goes down type of situation. So memorize this, Don't memorize your R, I'll give it to you.
Twinkle, twinkle, little star, how I wonder what you are. Up above the world so high, like a diamond in the sky. Twinkle, twinkle, little star, how I wonder what you are.
On the screen here you see 4 problems. I'll put these 4 problems also up on Moodle. This is what I want you to do over the weekend, okay? On the form, I'll put these 4 problems up also. I want your answers so that I see how you're doing. But these 4 problems with work, have them in your notebook so that I can help you on Monday know where you're going right or wrong. Give me your numbers over the weekend on the form so that I know beforehand in class which problems are very hard that we should spend time on and which problems you're just breezing through. Okay? Do some work. Enjoy your weekend. I'll see you guys on Monday. I'll tell them to have a good day.
Did you?
Mm-hmm.
Have a good day.